Okay, 1.5 is all about continuity, and this section is going to be full of all kinds of definitions and theorems. So there's actually not going to be very many examples that we work out. It's mostly just going to be writing down some definitions and theorems. So I'm just going to go through them relatively quickly. So go ahead and pause the video and write stuff down when you need to. You should probably write down all of the definitions and theorems that we go over in this section. So first of all, continuity. A function f is continuous at x equals c if all of the following conditions are met. So first of all, f of c has to be defined, right? So f has to exist at x equals c. Second of all, the limit as x approaches c of f of x also has to exist. And third of all, the limit has to equal the function value, right? So f is continuous if all three of those conditions are met. F of c has to be defined. The limit as x approaches c has to exist. And then the limit has to equal the function value. If any of those conditions fail, then f is said to have a discontinuity at x equals c. And here are a few different kinds of discontinuities that you could come across. So this first one is called a jump discontinuity for, I think, pretty obvious reasons. It's like you're on this half of the graph and then you jump to the next one. But there's a discontinuity here, right? Because f of c is defined, right? So that's fine. Condition 1 is met. F of c is whatever that value is right there. But condition 2 fails, right? Because limit as x approaches c of f of x does not exist. From the left, you're approaching this value. From the right, you're approaching a different value. And so condition 2 fails. This one is called an infinite discontinuity, again, for, I think, pretty obvious reasons. So you have an infinite discontinuity at c. And on this one, it's actually condition 1 that fails, right? F of c is not defined at all. Okay. Limit as x approaches c, well, it exists if you consider infinity to be kind of an appropriate limit. We've been treating that as, we would say the limit as x approaches c here equals infinity. But definitely f of c does not exist. And then this third type is called a removable discontinuity. And you might have a homework problem or two that kind of explains why that's called a removable discontinuity. But let's see what fails here, right? So in this case, f of c is defined, right? F of c is whatever that value is right there. Limit as x approaches c also exists, right? From the left, we're approaching this value. From the right, we're also approaching this value. So that limit exists. What fails here is condition 3, right? The limit, which is this value, does not equal the function value, which is that one, right? So anyway, so this one fails condition 3. Let's look at some more examples. So, is the function continuous at x equals 2? Okay, so is the function continuous at x equals 2? And we're going to look at a few of these. Let's do f of x equals x squared minus 4 over x minus 2. So, is the function continuous at x equals 2? Well, the first thing we would want to do is see if f of 2 is defined. F of 2 in this case would be 2 squared minus 4 over 2 minus 2. That's 0 over 0, undefined. So no, right? We don't even need to check the other two conditions. We already know the answer to part A is no. Okay? Well, let's see if we can fix it up a little bit. So let's let g of x let's let g of x be this piecewise function, x squared minus 4 over x minus 2 if x is not equal to 2, and then 3 if x does equal 2. So is that function continuous at x equals 2? Well, let's see. So checking the first condition, g of 2. So g of 2, if x equals 2, then we use the bottom rule, right? So g of 2 equals 3. Okay, so that value is defined. Condition 1 is met. Condition 2. We need for the limit as x approaches 2 of g of x to exist. So we need limit as x approaches 2 of g of x to exist. Well, so let's think about this. What is the limit as x approaches 2? When x equals 2, we use the bottom rule. But for every other value, we use the top rule. The limit as x approaches 2, we would be looking at values slightly bigger than and slightly smaller than 2. We wouldn't be using it 2 exactly. So for all of the values that we would be using, we would be looking at the top rule. So this is equal to the limit as x approaches 2 of x squared minus 4 over x minus 2. Now if we plug in 2, we're going to get 0 over 0, which is undefined. But what that tells us is that we can factor, right? So this equals limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. And the x minus 2's cancel. We get limit as x approaches 2 of x plus 2, which is 4. Okay, so the limit exists. So the function value exists and the limit exists. Now condition 3 is that those two values need to be the same, right? So we need g of 2 to equal, we want to know, does it equal the limit as x approaches 2 of g of x? And the answer is no, right? This condition is not met because g of 2 is 3, and limit as x approaches 2 of g of x is 4, right? So the answer to part B, is this thing continuous at x equals 2? The answer is no. Okay, but let's look at a third example. So this time we're going to let h of x be this piecewise function, x squared minus 4 over x minus 2 if x is not equal to 2. And then it's going to equal 4 if x does equal 2. And the question is that continuous at 2? Well, first thing we would need to check is h of 2. Does h of 2 exist? And the answer is yes, right? H of 2 is 4. When x equals 2, we use the bottom rule. What about the limit? Limit as x approaches 2 of h of x. Does that exist? Well, if x is not exactly equal to 2, then we would use the top rule. So this is the same thing as limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, so we just did this, right? Okay, so the limit exists, right? The function value exists, the limit exists. Is the function value equal to the limit? And in this case, yes, right? The function value and the limit are the same value, right? So does h of 2 equal limit as x approaches 2 of h of x? And the answer is yes, right? 4 equals 4, so yes. All right, so the answer to part C, yes. Okay, h of x is continuous at x equals 2. Okay, so that's the idea behind continuity. Now, or rather, what I should say is that's the idea behind continuity at a point. But oftentimes we're interested in just the continuity of a function in general. Like we're interested in asking the question, is this function continuous on its domain? So let's talk about what that means, right? So if a function f is continuous at every point in some open interval ab, then we say that f is continuous on ab. Now, if in addition to that, the limit as x approaches a from the right-hand side, so if the limit as x approaches a from the right-hand side of f of x is equal to f of a, then we can say f is continuous on this half-closed interval, right? And similarly, if limit as x approaches b from the left of f of x equals f of b, then f is continuous on this half-closed interval. And of course, if both of those things are met, right, if both of these limits equal the function value at the endpoints, then we would say f is continuous on the entirely closed interval. Okay. So the main moral of the story is this is what it means for a function to be continuous at a point. If a function is continuous at every point within a particular interval, then we say that it's continuous on that interval. And if in addition to that, the function value matches the limit at the endpoints, then we can say that f is actually continuous on the closed interval as well. Okay? So, for example, let's show that f of x equals square root 9 minus x squared is continuous on the closed interval from -3 to 3. Okay, first of all, let me just point out that this is the domain of f. You can't plug in anything bigger than 3 or anything smaller than -3. Like if you tried to plug in 4, for example, you get 9 minus 4 squared. 4 squared is 16, right? 9 minus 16 is a negative number. Square root of a negative number is not real, okay? And in this class, we're only dealing with the real numbers, okay? Complex analysis is a whole different ballgame, okay? So we're only dealing with this on the real numbers, which means x has to be 3 or less. Maybe a better way to say it is x has to be bigger than or equal to -3, but less than or equal to +3. That's the domain of that function. You may recognize this as a semicircle. So from previous algebra classes, you may recognize that this is the upper half of a circle. Oh, I should go 1, 2, 3 as well. But yeah, it's the upper half of a circle, right? So that's what that function looks like. Okay? So let's show that this is continuous on this interval. So the first thing we should do is show that this thing is continuous just at an arbitrary point inside of this interval. So we're going to go through those same 3 conditions that we looked at before. We're going to look at f of c. That's going to be square root of 9 minus c squared. Okay, but that's perfectly well defined as long as c is inside of this interval, right? So this is defined, sure. It's a real number, yep. Okay. Sorry, I need to pause the video for a second. Okay, so f of c is defined. The next thing we need to do is figure out, does the limit as x approaches c exist, right? So limit as x approaches c of f of x. Well, I should have just written the function out, right? This is limit as x approaches c of 9 minus x squared. We're not going to get any domain issues, as you know, again, as long as c is within this interval. So we can just go ahead and replace x with c. We're going to get square root 9 minus c squared. So yeah, that limit also exists. And then the third thing is that f of c has to equal limit as x approaches c of f of x. Well, f of c is square root 9 minus c squared. Limit as x approaches c of f of x is square root of 9 minus c squared, right? So that condition holds. So since those three things hold, we know that we can say, therefore, f is continuous on the open interval from -3 to 3. Now the question is, what happens at -3 itself, and what happens at 3 itself? So in order to show that this function is continuous on the closed interval, we also need to make sure that limit as x approaches -3 from the right-hand side of f of x equals f of -3. So we need to see if this is the case. Well, let's see. We can make a table of values or something. I mean, we could plug in. So let's think about this, right? If we're approaching -3 from the right-hand side, we would be plugging in values slightly larger than -3, so like -2. If I plug in -2, -2 squared is 4. 9 minus 4 is 5. Square root of 5 is, I don't know, something slightly bigger than 2. Okay? Something slightly bigger than 2. If I plug in something a little closer to -3, like -3 or -2.5. So -2.5 squared, -2.5 squared, 6.25. 9 minus 6.25 is 2.75, right? And the square root of 2.75 is, you know, something like 1.7-ish. So the value is decreasing for sure. It's decreasing. Now, what happens if I were to just directly substitute -3? -3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0. It's perfectly well defined. So yeah. Limit as x approaches -3 from the right, I would say, is 0. Meanwhile, f of -3 is what you get when you just directly substitute -3 for x, and you're going to get 0 for that as well. Okay, so that condition is met, and so that means f is continuous on -3, 3. So then the last condition we have to check is to make sure that the limit as x approaches 3 is equal to f of 3. So from the left, right? We have to be approaching from the left because the function is not defined for x greater than 3. But let's see. Is this equal to f of 3? Well, yeah, by a similar line of reasoning, right? It's like if we plug in 2, we know we're going to get square root of 5. If we plug in 2.5, we know we're going to get square root of 2.25, I believe it was. You know, and we can keep getting closer and closer and closer to 3. But by the time we get to 3 itself, we're going to be all the way down to 0, which is the same as what we're going to get when we directly substitute 3. So yeah, the limit equals the function value. So therefore, f is continuous on -3 to 3. Okay, so maybe a little bit of a silly example, but that's the idea, right? A function is continuous on a particular interval if it's continuous on every point in that interval. So these conditions are sufficient to show that it's continuous on the closed on the open interval. Then if you want to show that it's continuous on the closed interval, you just have to check the endpoints as well. Okay? Let's do another one. Or let's, by another one I mean, let's look at another theorem. I told you this section is just full of definitions and theorems. Okay, so the next theorem, kind of a nice one, says if f and g are both continuous at C, then f plus g is continuous at C, f minus g is continuous at C, f times g is continuous at C, and even f divided by g is continuous at C, provided that g of C is not equal to 0. Okay? If g of C does equal 0, then f over g has a discontinuity at C. Okay? So sometimes we call this the algebra of continuous functions, right? The sum of two continuous functions is continuous. The difference of two continuous functions is continuous. The product is continuous. And the quotient is continuous as long as g of c is not 0, right? As long as the denominator is not 0. As a corollary to that, any polynomial is going to be continuous everywhere, right? Because a polynomial is just a sum or a product or a difference of x and some constant values, which are continuous functions, right? They're continuous everywhere. So polynomials are continuous everywhere. Rational functions are also continuous everywhere, except at the points where the denominator is 0. So where the denominator is 0, that's where you're going to have some discontinuities. So for example, let's find the discontinuities of this function here. Someone is screaming in my household like a wild savage. Okay. Where are the discontinuities of f of x? See, this is what happens when you're on lockdown, right? And like everyone's at home together. People just go crazy. And I'm the only one who gets any work done. Everyone else just playing around. How fair is that? Anyway, so example 3, where are the discontinuities of this function? Well, this is a rational function, right? It's the ratio of two polynomials, and we know from the corollary that we just looked at that rational functions are continuous everywhere, except for where the denominator is 0. So the discontinuities are going to take place whenever x squared minus 5x plus 6 is 0, right? So this is equivalent to asking, where is x squared minus 5x plus 6 equal to 0? Well, we can factor that. And then we can solve, right? So x equals 3, x equals 2. So you have discontinuities at x equals 3 and x equals 2. I guess I could have labeled them in order, right? X equals 2 and x equals 3. Whatever. It doesn't matter. Okay. So that's nice to know. Anytime you see a polynomial, you know that it's continuous everywhere. Anytime you see a rational function, you know that it's also continuous everywhere except for where the denominator is 0. That means there's not going to be any holes or jumps or anything in the graphs of polynomials or rational functions, except in the case of a rational function where the denominator is 0. Here's another useful fact. If limit as x approaches c of g of x equals L, and if f is continuous at L, then limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x. In other words, you can take that limit and you can move it inside of the function value, which is really pretty nice. I mean, limits they just behave so nicely for us, right? So you can take that limit and you can move it inside, provided that this limit exists and that f is continuous. But I'll give you an example of this. So it allows us to find limits of certain functions a lot easier than we would otherwise be able to do, right? So for example, given that limit as x approaches 1 of 3 to the x minus 3 over 5x minus 5 equals 3 times the natural log of 3 divided by 5. And this is a true statement, by the way. Okay? And this is not 3 times x, it's 3 to the x power. Okay? But given that this limit is equal to 3ln 3 minus, or 3ln 3 over 5, let's calculate the limit as x approaches 1 of the square root of 3 to the x minus 3 over 5x minus 5. Well, what the previous theorem tells us is that we can take this limit, which is sitting on the outside of this function, and we can move it to the inside of the square root function there, right? So we can call this the square root of the limit as x approaches 1 of 3 to the x minus 3 over 5x minus 5. And how does that help us? Well, that helps us because we know that this thing is 3ln 3 over 5. So this should just be square root of 3ln 3 over 5, whatever that is. Right? You could pop that into your calculator to see approximately how much that is. But anyway, that's a really nice property. Okay, that's a really nice property of limits. Now here's a corollary to that, which has to do with continuity, right? So the corollary says if g is continuous at c, and if f is continuous at g of c, then f of g is continuous at c. Right? A little bit of, just a little note about that. So note that f of g of c is f of g of c. So in case you're a little bit rusty with your composition notation, that's what we're saying. And that's why the corollary says what it does, right? First of all, g of x has to be continuous at c. And then, if that condition is met, it also has to be the case that f of x has to be continuous at g of c. All right? But as long as those conditions are met, so if g is continuous at c, and if f is continuous at g of c, then f of g is continuous at c. Right? That's what that corollary is saying. Maybe a less precise way, but more understandable way of saying this is that the composition of two continuous functions is a continuous function. Okay? So the composition of two continuous functions is a continuous function. For example, what would be a good example? We just showed that square root of 9 minus x squared is continuous. So f of x equals square root of 9 minus x squared is continuous. We've also shown that any polynomial is continuous. So maybe we could say g of x equals 2x plus 5 is continuous. So therefore, f of g of x, which equals f of g of x, which equals square root of 9 minus 2x plus 5 squared, is also continuous, right? It must also be continuous. Now, if you wanted to answer the question, but where is it continuous, right? It's like f is continuous between -3 and +3. this thing is not necessarily continuous in the same locations. Okay, so in particular, what you would need is you would need the domain. You would need to look at the domain, but this thing is going to be continuous on its entire domain. Okay, so that's what that corollary is saying. Here's another theorem. This has to do with inverse functions. Okay, if f is 1 to 1, remember that a 1 to 1 function is a function that has exactly one input value for every output value. Okay, so something like f of x equals x squared is not 1 to 1, because if you look at the output value 4, there are two input values that lead to it, -2 and +2. So that would not be a 1 to 1 function. But something like, you know, a straight line or like a cubic function, right? These things would be 1 to 1. Anyway, so if f is 1 to 1, then it has an inverse. Okay, and this theorem is going to tell us what we can expect about its inverse. So if f is 1 to 1 and continuous on its domain, then f inverse is continuous on its domain. And you may recall from previous algebra classes that the domain of an inverse is the same as the range of the original. So if f inverse is continuous on its domain, that's the same thing as saying that f inverse is continuous at each point on the range of the original parent function f. So if f is 1 to 1 and continuous, then f inverse is also continuous. Okay? So here's another example. So let's show that f of x equals x cubed plus x has an inverse. And once we've completed that task, then let's answer the question, is f inverse continuous on the interval -infinity to infinity? Okay. Okay, so let's do this. So for the first task, right, show that f of x equals x cubed plus x has an inverse. Well, if f of x is 1 to 1, then it has an inverse. So this is the same thing as trying to show that the function is 1 to 1. One way that we can justify that f of x here is 1 to 1, well, there are a couple ways. I mean, you could look at a graph of it. So you could think back to like your pre-calculus days and how we graph polynomial functions like this. Excuse me. Or you could like open up a graphing calculator like Desmos or something, right? And look at the graph. But assuming that you didn't have access to a graphing calculator or whatever, to show that this has an inverse, one thing we could do is to reason out that this thing is going to be strictly increasing, right? So imagine, like, if you plug in, you know, -5, you're gonna get -5 cubed, which is -125, minus 5, so you're gonna get -130. Now, if you plug in -2, you're gonna get -8 minus 2, which is -10, right? So you increase from -30 to -10. If you plug in 0, you're gonna get 0. If you plug in 10, you're gonna get, oh, maybe something smaller. If you plug in 4, you're going to get 4 cubed plus 4, so that's going to be 64 plus 68, right? So it's a strictly increasing function, right? As x increases, x cubed will increase, and so will x, and so therefore the sum will be increasing. So note that f is strictly increasing. And we can give a little proof of that, I guess, right? So we can say, right, if x1 is, maybe I'll say it like this, if x2 is greater than x1, then x2 cubed is greater than x1 cubed. So x2 cubed plus x2 is going to be greater than x1 cubed plus x1. So in other words, f of x2 is greater than f of x1. Right? So, so f is strictly increasing. What does that tell us? So since f is increasing, it must be 1 to 1. Well, why is that? Well, because if x is strictly, or sorry, if f is strictly increasing, like a one-to-one function would fail the horizontal line test. And in order to fail the horizontal line test, that would mean that the function would have to double back on itself like that before going back up. Some cubic functions do this, right? But that's not the case here. Notice that this would fail the horizontal line test, and you know that that doesn't happen because f is strictly increasing. So here we're increasing, but when we start to drop again, we're decreasing, right? Before we increase again. And we know that this part doesn't happen, right? It doesn't happen because f is a strictly increasing function. Okay? So since f is strictly increasing, the only way to draw the graph would be something like that. So it's not going to fail the horizontal line test. It must be 1 to 1. And so then finally, since f is 1 to 1, it has an inverse. Okay, so first task is done, right? Show that f of x equals x cubed plus x has an inverse. We're done, right? F of x has an inverse for sure. Now the next task is to answer the question, is that inverse continuous on all real numbers? Well, f of x is a polynomial, so f of x is continuous. The range of f of x is all real numbers. So that means f inverse of x is continuous on all real numbers. Yes, right? So by the previous theorem, since f is a polynomial, it's continuous. So this is, I'm answering the second question now, but since f is a polynomial, it's continuous. Therefore, f inverse is also continuous. Since the range of f is negative infinity to infinity, the domain of f inverse is negative infinity to infinity. Therefore, f inverse is continuous. We know that f inverse is continuous, and we know that its domain is negative infinity to infinity. So f inverse is continuous on negative infinity to infinity. Okay, so the answer to the question is yes. Okay, so yes is the answer to that question. Okay, we've got one more theorem and a corollary, and then one last example, and then we'll be done with this section. So last theorem. This is an important one. It's called the intermediate value theorem. So it has a special name. You know, any theorem with a special name is an important theorem. So this is the intermediate value theorem, and if we refer to it again in the semester, which we probably will, we'll just call it the IVT for short. Okay? But the intermediate value theorem says if f is continuous on some closed interval from a to b, and k is any number between f of a and f of b, then there's at least one number x in the interval a, b, such that f of x equals k. Here's what we're trying to say. So here's a picture, right? So let's say you have some function, right? Doesn't have to be one-to-one, right? This one's not one-to-one. But it does have to be continuous on the closed interval from a to b. So it's a continuous, smooth curve, no holes, no jumps, nothing like that, right? From a to b. Now, let's say that, so f of a is down here, right? F of a is down here, and f of b is up here, right? So if you choose any value k between f of a and f of b, then since f of x is continuous, there has to be some point where f of x crosses this line. And that's x, right? So for any k between f of a and f of b, there must be an x so that f of x equals k, right? It's got to be the case. That's what the intermediate value theorem is telling us. Now, as a corollary to that, if f is continuous on AB, and if f of a and f of b have different signs, then there's at least one solution of f of x equals 0 in the interval from a to b. Okay? So maybe to draw a little picture of that, it's like, so imagine maybe a is here and b is here, and you've got f of a is negative, f of b is positive, and you're continuous from a to b. Well, that means you must cross the x-axis at some point, right? So there must be a point x at which f of x equals 0. Gotta be, right? So that's what the corollary is saying. So to show you an example of this, we can approximate some zeros. So let's approximate the 0 in the interval 1, 2 of p of x equals x cubed minus x minus 1. Maybe before I finish writing the problem, actually let me finish writing the problem first. Let's approximate the 0 in this interval of this function to 2 decimal places. All right, to 2 decimal places. Okay, so now I'll say what I was going to say. If you try to find the zeros of this function directly, you're going to struggle because there aren't any rational zeros, okay? So they're particularly difficult to find. But the good news is that we can approximate those zeros to any desired level of accuracy, and in this case we're going to approximate them to 2 decimal places. So let's do it. Okay, so approximating this to 2 decimal places. We're told right away that, that there's a 0 in this interval between 1 and 2. What that means is that f of 1 and f of 2 should have different signs. So I'm going to use my calculator a lot here. So let me see what f of 1 is. I could do this in my head, but it's useful to just have it in my calculator. All right, so f of 1 is equal to negative 1. F of 2 is equal to 4. Sure enough, you have different signs, and this is a continuous function, which means f of x must be 0 somewhere between 1 and 2. So I could say there's a 0 between x equals 1 and x equals 2. Well, we already knew that going into the problem, but let's try to narrow down where that 0 is. So I might plug in a value in between those, like f of 1.5. let's see what we get. F of 1.5 is negative 0.125. What does that tell us? Well, notice that the sign of f of 1 and the sign of f of 1.5 are the same. So the 0 is not there. However, the sign of 1.5 is negative, and the sign of f of 2 is positive. So there must be a 0 between 1.5 and 2, right? So we can make it a little more exact. We can say there's a 0 between x equals 1.5 and x equals 2. So you see we've narrowed it down. Here the length of our interval was 1. Here it's only a half. So we're getting warmer, you might say. So we choose a value in between here, maybe, I don't know, 1.7 or something. Hang on a second. Oh, I've got a problem. I'm sorry. Let me go back and amend a little bit. This should have been 5, not 4. And this should have been positive 0. Okay, so this should have been positive 0.875, which means this statement's not true anymore. Okay, sorry, I punched in the wrong number into my calculator. Okay, so actually f of 1.5 and f of 2 have the same sign. So the place where the function changes sign is somewhere between x equals 1 and x equals 1.5. So really we should say, okay, there's a 0 between x equals 1 and x equals 1.5. My apologies. You're probably like staring blankly at the screen like, what is he talking about? But anyway, so these are the correct values now. Well, okay, so let's choose a value between 1 and 1.5, like maybe 1.2. Let me enter this more carefully. 1.2 cubed minus 1.2 minus 1 is negative 0.472. Okay, so I'm negative at x equals 1, and I'm still negative by the time I hit 1.2. So that tells me there's a 0 between x equals 1.2 and x equals 1.5. Okay, so let's check. Well, maybe let's check 1.3. F of 1.3. Okay, still negative. Negative 0.103. Let's check 1.4. Ah, there we go. Positive 0.344. So notice that f of 1.3 is negative, f of 1.4 is positive. That means there's a 0. So there's a 0 between x equals 1.3 and x equals 1.4. Okay. So we want to approximate the 0 to 2 decimal places, so we need to get even more accurate. Here's what I'm going to do. I'm just going to cut to the chase and make a little chart. I'm going to say 1.3 on one end, so I'm going to put x here and f of x down here. I'm just going to make a chart. 1.31, 1.32, 1.33, and so forth. .39 and then 1.4. Okay, and then I can go back into my calculator, or if you're like really clever with Excel or something, you could probably do these all at once or whatever. But let's go back in. Actually, I know what 1.3 is. I know that it's negative 0.103, and I also know that this is positive. But I want to figure out where the change occurs. So I'm going to go back in and put in 1.31. That's still negative. I don't really care what the value is. I'm going to put in 1.32. Still negative. I'm going to put in 1.33. Positive. There we go. So there's a 0 between 1.32 and 1.33. Okay, so we could keep going like this. Your book uses a convention that the book says is common practice. I'll have to take the book's word for it because I don't really know. But it says that the common practice is if you want to approximate to the nearest or to 2 decimal places, then what you really do is you get down to this point and then you just say that the 0 is exactly halfway between. So you'll say that the 0 is approximately 1.325, right? And then they say that's the answer to the question. It's kind of a strange convention if you ask me, but the idea is that this way you're sure that your error is no more than 0.005, which if you round to 2 decimal places, I guess 0.01. I mean, so I guess that your error is no more than, you know, you're not going to be off by, well, shoot, how would you say that? You're not going to be off by more than 0.005, I guess is the best way you can say that. So anyway, but that's that. So that's the 0 approximated to 2 decimal places, even though your answer has 3 decimal places in it. But that's what the book's going to look for. And that's all I have to say about this section. It's about time too, huh?